Okay, let's look at some examples from your homework. And I want to start with number 15. Number 15 is just your basic calculate this definite integral or evaluate this definite integral. And so we're going to be using the fundamental theorem of calculus in order to do this. So this is your chance to kind of watch the fundamental theorem of calculus in action. But I wanted to go through this one specifically because this one can be a little tricky to kind of see what the function actually is. So if I take a look at this, I've got the cube root of x squared minus 3 over the cube root of x. And remember, in order to use the fundamental theorem of calculus, I need to be able to find the antiderivative of this function. But you might look at that and say, holy moly, I don't know the antiderivative of a function like that. That's way too complex. Well, let's take a look at this function a little bit. Is there anything we can do to this function to simplify it? Well, I have subtraction in the numerator, and I just have a single term in the denominator. That means I can actually split this up into two different fractions. Two different fractions that have the same denominator. So these fractions have a common denominator of cube root of x, and if I wanted to, I can combine them, and when I combine them, I'm just back to where I started. So I split this up into two different fractions, and now, what do we notice? Well, let's take a look at this second term to start out with. I've got 3 over the cube root of x. Well, what is the cube root of x? The cube root of x is just an exponent. I could rewrite this as 3 over x to the 1/3. Remember, roots are just fraction exponents. Well, if I have x to a power in the denominator, I can move that to the denominator by just making the exponent negative. So this is the same thing as 3x to the negative 1/3. And once I've written it like that, that's just a power function. So at this point, I should be good. I know how to find the antiderivative of that. So now let's focus on the first piece. Once again, we need to recognize cube root as an exponent. This is the same thing as x squared raised to the 1/3 over x raised to the 1/3. Now, if you remember exponent rules, if you have two different things raised to the same power that's being divided, you can pull that exponent of 1/3 out and just focus on the fraction first and then raise it to the 1/3 power. Why is that helpful? Because what's x squared over x? That bottom x cancels out with one of the x's in the numerator. All you're left with is just x over 1 raised to the 1/3. And what's x over 1? X over 1 is just x. So I'm left with x to the 1/3 minus 3x to the negative 1/3. Both of those are now power functions, and I have an antiderivative rule for power functions. So with a little bit of algebraic manipulation, I was able to rewrite my function in a way that is much simpler, in a way that I know how to find the antiderivative of it. So I can now rewrite this definite integral like so. Definite integral from 1 to 8 of x to the 1/3 minus 3x to the negative 1/3. This is the same function as what I started out with, it's just written differently. Now, using my definite integral properties, I can split this up into smaller definite integrals in order to evaluate this. So now that I've split up into smaller pieces, now I can just focus on, hey, what's the antiderivative of x to the 1/3? Well, I add 1 to the exponent and divide by my new exponent. So I'm going to divide by 4/3. Remember, dividing by a fraction is the same thing as multiplying by its reciprocal. So instead of dividing by 4/3, I can multiply by 3/4. So there's the antiderivative, but I still need to plug in the bounds. So to show that, what I do, I replace my skinny s with just this straight line with my lower bound and then my upper bound. What that does for me, this notation is there so that you can, this is for after you found the antiderivative, but you haven't plugged in the bounds yet. So it's a notation I like to use. Okay, this other one, x to the negative 1/3 plus 1 gives me x to the 2/3. And then, of course, I'm going to divide by 2/3 or just multiply by 3/2. And that still needs to be evaluated from 1 to 8. Okay, so now I'm ready to plug in my bounds. So if I just focus on this first one, what is that going to look like? I'm going to take my upper bound and plug it in. So I'm going to do 8 to the 4/3 minus, and then I'm going to take the same antiderivative, but now plug in my lower bound. And that takes care of that first piece. And then I'm going to do the same thing with this second piece. I'm going to plug in the upper bound to my antiderivative, and then plug in the lower bound to the antiderivative and subtract the two. And now let's see what we get. Well, 8 to the 4/3 is just 16, so I get 3/4 times 16 minus 3/4. 1 to the 4/3, 1 to any power is just 1. So that's the first part. And for the second part, I get 3/2. 8 to the 2/3 is 4, minus 3/2. 1 to the 2/3 is still just 1. Simplify this a little bit more. I get 12 minus 3/4 minus 3/2 times 4 is 6. So I get minus 3 times 6 minus 3/2. Distribute that negative 3, and I get 12 minus 3/4 minus 18 plus 9/2. Simplify it, add my fractions, and I get negative 6 plus 15/4, which ends up equaling 2.25. So there's my antiderivative. So just a reminder of what we did here. Because this initial function is so overwhelming, use some exponent properties to rewrite this in a way that just is in terms of power functions. And once you have it in terms of power functions, then I can find my antiderivative and use the fundamental theorem of calculus, right? You find your antiderivative and then you plug in both bounds and subtract those values. This is the most complex of the problems that you'll have on the homework, so you'll have plenty of other simpler examples to practice this process of the fundamental theorem of calculus. But speaking of kind of tricky problems to start out with, if you just take a quick look at number 10 on your homework, number 10 has a function like this, and you might look at that and say, how do I find an antiderivative of something like that? Well, to do this, remember a square root, once again, is just a power function, a fraction exponent. And I can use a very similar exponent property that I used in this problem to just split this up into 7 to the 1/2 times x to the 1/2. Why is that helpful? Because this right here is just the square root of 7. That's a constant. You can pull it out in front of your integral and just move on. So hopefully that helps with number 10. Okay, for the next example I want to look at, I'm actually going to look at two different problems that are right next to each other. Number 13 and number 14. And the reason why I want to look at two of them at the same time is because this is our chance to really be able to analyze whether it's asking me for an indefinite integral or a definite integral. And really what it boils down to is, do you have bounds that you're looking at? So take a look at this first one. Find s of t. Remember, s represents the position function, v represents velocity, and a represents acceleration. Where it gives me my acceleration function, and then it gives me these two pieces of information. Well, if I take a close look at what that stuff is saying, these are both initial values. And they're initial values for different things. This represents an initial velocity, and this represents an initial position. How do I know that? Because both of these have 0 plugged in, meaning it's a starting value. It's an initial velocity and an initial position. So what is this problem really asking me to do? This is asking for an indefinite integral. Why? Because if I take the indefinite integral of my acceleration function, that gives me the antiderivative. That's going to give me the velocity function. This is going to give me the velocity function. And remember, when I take an antiderivative, I'm just going to do it real quick, we always have to put a little plus c at the end. But we talked about this back in 4.1. In some cases, if it gives me extra information, I can figure out what c has to be. And in our case, since this first antiderivative represents my velocity, this c right here is going to be my initial velocity. So my velocity equation is negative 9t squared plus 2t plus 10. So how do I find my position? I'm going to do this again. I'm going to take the antiderivative. I'm going to take the indefinite integral of my velocity function and see what it gives me. This will be my position function. Once again, I'm going to do this pretty darn quick. And so I get negative 3t cubed plus 2t squared over 2, which is just t squared, plus 10t plus c. Do I know what c has to be? I do, because I'm given an initial position. So My position function is negative 3t cubed plus t squared plus 10t plus 2. So those initial values aren't bounds. They help me figure out what c has to be when I take the antiderivative. So what about number 14? How is this one different? A particle is released as part of an experiment. Its speed t seconds after release is given by this velocity function, negative 0.3t squared plus 12t, where v of t is in meters per second. And then part A is asking, how far does the particle travel during the first 3 seconds? So, is this a definite integral or is it an indefinite integral? Couple of things you can ask yourself to be able to figure out which one. First off, is it asking me for an equation or is it asking me for a number? Notice the last example it was asking me for an equation. It was asking me what the position function actually is. And that's why we were finding an indefinite integral. But in this example, it's asking how far does the particle travel? What's the distance? What's the actual number? So this is a definite integral. Well, remember, in order for it to be a definite integral, I have to have bounds. That's the other thing you can ask yourself is, do I have bounds? Do I have a set starting point and do I have a set ending point? Well, if I'm looking at the first 3 seconds, what am I starting at? I'm starting at 0. What am I ending at? I'm ending at 3 seconds. So I have set bounds. And what am I integrating? I'm integrating the velocity function. Why? Because remember, the area under the curve of a rate function gives me total change. And that's the case here. If I integrate velocity, it gives me total distance that I've actually traveled over that time period. Just like the example we looked at in 4.2. So since this is a definite integral, I can just use the fundamental theorem of calculus. So I find my antiderivative, which is negative 0.3t cubed over 3 plus 12t squared over 2. I can of course simplify that, but then I need to evaluate it from 0 to 3. Let me simplify a little bit. I get negative 0.1t cubed plus 6t squared. And now I can go ahead and plug in my bounds. I'm going to start by plugging in the upper bound, and then I'll also plug in the lower bound, and I'll subtract those values. So when I plug in 3, I get negative 2.7 plus 54. What happens when I plug in 0 to this? I just get 0, which is kind of nice. So I'm left with 51.3. Well, look at part B. How far does it travel during the second 3 seconds? Very, very similar question. What's changing here? The only thing that's changing are my bounds. If I'm looking at the second 3 seconds, what am I starting at? I'm starting at 3 and going to 6. Other than that, it's the same exact process. I'll let you do that one on your own. But that takes care of, those are the examples that I wanted to look at for 4.3. Good luck with the rest of the homework, and if you still have questions, of course, feel free to reach out. Good luck.